We're here to talk about ML today. So, I'm Andy. I work in Netdata on ML, and we are a open source metrics and monitoring agent. You can scan this QR code for the slide there and stuff if it works, and then everything else is, all the links are there. So when I first submitted the abstract, I kind of thought it has a little bit of a listicle vibe, 10 practical ML use cases in observability. So I decided to sort of lean into the whole listicle vibe and go with a sort of a BuzzFeed approach to this. And I've tried to fit as many memes as I can on each slide, so we'll see how it goes. But so the new talk today is, you won't believe these 10 amazing AI use cases in observability. So we're talking about AI today, no longer ML. So I've got like 10 different use cases to get through. They're kind of like recipes, and that's, to be honest, like that's what a lot of ML is. It's just recipes, inputs, outputs, and how you put it together. So we'll see how far we can go. I'm not sure if I'll get all 10 of them covered, but I'll try and be pretty quick. And feel free to ask questions at any point. Like we can keep it nice and informal. So first, I've got one slide, some things to bear in mind. So there's a couple of themes here. So I have a couple of hot takes. Number one hot take is that observability is actually a little bit lags in when it comes to ML for like using ML to help us do our jobs. It's changing a little bit in the last kind of year or two, but generally it's always struck me as how other industries, like you look at like banking, advertising, entertainment, tech in general. ML is just like part of the furniture. It's just a tool you use. Whereas in observability, it still seems to be sort of like a selling point, which is a bit weird. Especially considering we have a lot of fancy plumbing and we have all these, which gets into this kind of the picture in there, which is this is the famous black box Google picture where from their paper they wrote up a paper of like what's involved in getting ML into production, and it turns out the ML part is just this little black box in the middle, and it's all the other stuff around it. The infrastructure serving, the data collection, validation. That's actually where all the hard work is. And it's funny because that's something that we all, like, observability is great at all that other stuff. That's part and parcel of what observability does. So I always found it kind of a little bit interesting that we don't sort of have ML as just like a de facto standard for most products in observability. But it's changing. It is improving the last couple of years. It's more commonplace now. And so. One of the other themes, so hot take number 2 is ML as UX. So there's a couple of examples where I'll show what I mean by that, but this is basically where in observability we have, you have a screen, you put something on the screen, sometimes it's like dashboards, some human has designed what goes where. We can use ML to sort of augment that whole flow basically where, you can actually have ML surface, data points to you as opposed to relying on how the screen is actually configured in the first place. And then number 3, design is hard, ML is easiest. So like, there's a lot of low-hanging fruit. Sometimes to get started, the ML itself, ideally, if you're not like embarrassed by your first ML implementation, then you haven't done it right. Like the whole idea is use as simple as ML as you can get away with, and then the hard part is actually designing the inputs, the outputs, how it all hangs together, and what the actual value is to the user, basically. And data products are still cool. So data products were very kind of hot a couple of years ago. They seem to be less talked about now. But basically, I consider everything a data product. And you need to focus on the data product. Like, what is the data product you're building? And then once you figure that out, then you can kind of ask, well, how can I use ML for that? Maybe I shouldn't use ML. Maybe I don't even need ML. And then some less kind of controversial stuff. Human in the loop, always, especially with observability. And I'm particularly focused on metrics with some of this stuff, but it's not just metrics. It can be, logs, traces, events, anything you want, really. And self-driving observability is no. We don't have that. And it's looking like it's getting further and further away as kind of systems get more and more complex. So if anyone tries to sell you automated root cause or any of these kind of buzzy marketing terms, be very, very wary. So Number one is probably a common one, probably the most familiar one. Is my data normal or strange in some way? And then you kind of have to think about, with each of these kind of questions, what data, what do you mean by normal, how strange, and in what way? And so this is the anomaly detection use case, basically, which is kind of, this is probably the most standardized way that ML is used in observability at the moment. So the inputs here in this particular example are like your metrics. The output is an anomaly score at each time step. So some score basically that measures how strange or how anomalous something might be. And then how you do it, there's 3 main ways to do it. You can use rules, you can use stats, like z-scores and things like that, or you can use ML, which is what kind of we use at Netdata. And so there's some examples of different types of anomalies. We're not just talking about like strange outlier points. There's all different ways that your metrics can be anomalous, and there's some examples there. And some of the main kind of things to think about there is like the number one decision point is forecasting versus supervised. So typically what a lot of people do is they use they try and predict the next value of the metric, say, and then see what happens, see what the next value was, and then look at the difference and the error, and that error then becomes an anomaly score, or you can, it's like you can do some post processing then as well. But another approach is to use an unsupervised approach, where you just look at the data and you have a measure of how strange it is. I think this is kind of simpler because this is like a smaller problem to solve. Solving forecasting, like forecasting, time series forecasting is like one of the hardest problems. No matter how much people kind of pretend like they can do it, it's actually really hard. So it's kind of hard to use, solve forecasting to actually do anomaly detection is a really hard problem. So we kind of take an unsupervised approach where we're just trying to get a good solid measure of when something looks strange. And then this is kind of common for a lot of these applications, is you have to ask yourself, where does the data live, where does the training live, and where does the scoring or inference happen? And so if you have the luxury of all the data living in the cloud in some big, cloud provider, then you can do the training maybe in the cloud provider. And if you even need to do, sometimes you might only do you might only need to do your scoring maybe once every couple of hours, because maybe you don't need real-time scoring. So then you have the luxury of, you can just throw the kitchen sink at it, and all your data lives in the cloud. You can do whatever fancy stuff you want. But then obviously, if in our case, we're using the ML. We need to do the scoring and the training on the agent in like real time every second as the metrics come in. And so that just changes the whole. That changes like the whole. What sort of methods you can use, and the trade-offs between basically compute and latency is a big kind of key trade-off there. So this is one that, like, some of these use cases we've built. Some of them are still sort of ideas, and we have proof of concepts out, and some of them are miles away. So this is one that we've actually kind of built, and there's some links there for. We actually have a blog and a video that goes through it all. And there's a Python notebook that sort of does it all in a nice kind of easy way to see how it all works under the hood. The next is sort of it's kind of like a subset, but it's a little bit different. So this is like, has anything changed? So typically you're looking, you've got some problem, for some reason you're in your observability tool, trying to figure out what's going on, and a lot of the times what you're really looking for as you're scanning through all these charts and dashboards is what's changed, basically. And you want to know what's changed. And it might not be an anomaly. Like, you might have changes like this that just happen all the time throughout the day. But they're not necessarily anomalous, but they are changes. So it's kind of, this is where I say it's like a subset. And the input here, again, is your metrics, and the outputs are, for each time, it's an index of ones or zeros to say, does this timestamp represent a change or not? And this one is, you can actually get very far with like statistical measures for this. Like median absolute deviation is one that's used, and this is another one that we've sort of built, and we use statistical sort of hypothesis tests to basically take a window of time before, take a window of time after, and just do a statistical test to see if it's statistically different basically in terms of the distribution. And that's pretty good at catching not just sharp changes like this, but also changes where the shape of the line has dramatically changed in a short window. And again, there's similar sort of considerations, like streaming versus batch is a big one here. So if you have do you have the full time series in your hands when you need to do this change detection, or do you need to do it as the data's coming in? That's kind of the main big kind of design choice here. And similar for compute overhead. You know, do you have, how much kind of compute overhead budget do you have? Do you have to be as lightweight as possible, or can you process some of these methods, they process the data once, then they take another run through it, and that's like expensive, but it might be more accurate. So there's trade-offs there. So the next one is what alerts are most important. So this is one that everybody, you know, we hear all the time about alert fatigue, too many alerts, and how to figure out which one you should look at first. And this is one that I don't know why this hasn't been sort of solved before, so it's a little bit of detail here, but basically if you think of an alert as like an advertisement basically, then if you kind of squint a little bit, you can actually turn alert ranking into like advertising CTR prediction. So the idea here is you have your inputs, which are alerts, your outputs, which are your probability that somebody actually clicks on that alert if they see it. And then you can literally do a binary classification, which is this sort of, basically you take all of your alerts that had clicks, you take all of your alerts that didn't have clicks, put them all together, and you can use that then to build a model to predict for each alert. Then you can kind of have a probability that somebody will actually click based on if they see it, based on what you actually observe them doing. And so this is one we haven't actually, we've kind of doing research on this. It takes a lot of time to obviously build up all these data sets of clicks, because most people don't really click their alerts, but once you have enough data, you can kind of have a model. And so like one way to validate if this works is what these charts are trying to show here at the moment, which is, this is like a random day of alerts, take all the alerts, score them all with the model, and then order them based on deciles. And you can see like in the top corner is the top 10% of probability scores, and they're like, those alerts that are in there, they get clicked on 76 times more than the alerts that are in the bottom decile. And you can see it's like a curve, as you would expect. So this could be good for, you know, filtering out alerts that are rubbish. The ones that are in the bottom 10%, they're probably mostly kind of rubbish. No one ever clicks them. And rubbish is hard, because what we're saying here is we're not trying to make a judgment on the alert. We're trying to say like interestingness, or because you could still have some alerts that are kind of significant, but this is more like a measure of you know, which ones do people more likely react to. So this is the tricky bit, as to how do you make this into a product then. You might say like it's a measure of, well, it is a CTR score, but you have to be careful about not, you know, it's not a measure of which alerts are more important than others. It's which ones are more likely to solicit some sort of action. So, and this kind of, the idea here is, again, similar with like marketing. If I could only show you N alerts, which ones should I pick, basically? And this is the idea here, where we can actually then have alert ranking, so that maybe you're more likely on average that it's in those top alerts that you're going to have the ones you're probably most likely to react to. And this is a good one. This is actually a real example where we can actually use LLMs and large language models and fancy stuff a little bit. And actually this is where like the fancy stuff can help you be a little bit lazy. So this is what we actually used here is we just take this text. So the text below the lines is basically this is the story of the alert. So the name is blah, blah, blah. The state is from, you know, state is from, state is to. The value is, the chart is. So this is like take all the structured data and make it into a little sort of paragraph for each alert. And then you can kind of just blindly dump this into a language model to fine tune, to see, okay, feed in the actual alert text, which is sort of like a template. It is structured, and then feed in the ones that are zeros if they were clicked or not, and that's what the model will actually learn on then. So you can kind of fine tune. This is an example of fine tuning large language models. We used Dilbert from Google. So the end result is, once that's trained, you have this probability, this prob click here. So you can see the one on the left has like an 80% probability of click according to the model. And I should say that this isn't a real probability. When we stack the positive alerts and the negative examples, we do a 50-50 balance. So that basically what you end up with then is you get a probability of about 50% from the model. That's kind of like meh, kind of average. Probability that's then higher, like 80%, it really thinks this one is important, and then probability that's really low, like this one that's on the right side, which is 6%, it says no one ever really clicks on them, you know. So what it's kind of saying is, like, obviously this system D, some service has started to fail. That's something that seems to be, people really seem to react to that, basically. And then the other one is, like, you know, MySQL slow queries, 25 slow queries, gone from clear to warning. it doesn't. It seems like, and you can see like the warning count and critical count is 0. So this is the other alerts on the node at the same time. So it's just this alert that's on at the moment. People don't tend to click it, so maybe we don't need to put this. These don't need to be next to each other at the top of your inbox, basically. Next one is which different patterns exist in my data. So this is basically a good example of the ML as UX stuff I was talking about. So this is where we know we have thousands of metrics, and what we really want to know, and kind of what we're trying to do in our head when we're looking through these, is to see which different patterns are in the metrics. So which ones are grouped together, and which ones kind of what sort of shape do they have, and which way are they grouped together. And this is like a perfect use case for clustering. So the inputs here are all your metrics, and the outputs is literally a cluster label per metric. So it's however many clusters you have, it's just an integer to say this is cluster 0, this is cluster 2, and then you can just do something like k-means. And so the big sort of DNA finger strippy thing on the side there is actually a heat map of I don't know, like 5,000 metrics on a node, a couple of nodes, and what you do is you actually sort the rows based on the cluster label, and then you can kind of see different patterns that appear. So you can see like which things are turned on at the same time, which things go off at the same time, and then you're looking for like columns as well. Columns represent metrics that all turn on together, and then there's like all sorts in between. So there's different sort of, you can kind of, this is like the highest bandwidth way to quickly just scan 4,000 metrics, and then obviously if you do this right, you can kind of zoom in and you could select all of the, that cluster that turned on there over time. Maybe you can look at that and see, or the ones that are on off, maybe you want to look at them. So this is an example where you're using the ML to surface the UX basically, in terms of like what is it I'm looking at. And this scales pretty well. There's only one little trick here, is you have to normalize all your metrics to do this, because all these metrics are on different scales, and so obviously you kind of need to normalize them beforehand. So you have to do this. You have to sort of get all the data and then do the normalization and then do the clustering. So this isn't one that you can't really do this in like a streaming sense or anything. Next one is which metrics must look most like this one. So this is kind of similar. It's a little bit similar, but oftentimes when you're looking at a metric and you're looking at a shape of a time series, and you're kind of trying to wonder what other stuff looks like this time series basically, and that's like easy. It's really easy in terms of ML. All you're doing here is you're looking for similarity scores. So your inputs are your metrics again, your outputs are your similarity scores. And it's just a distance measure, which is barely, this is barely even ML, this stuff. It's just the cosine similarity is kind of almost like a statistical measure. And the idea here is like, this is, so you can see the chart on the top there, this is the target metric. So you always have to start with one time series or one metric, and then you say, you can either use the whole time series, or you can highlight a particular region and say, show me everything that's similar to this candidate basically. And then so you can see here, like, obviously it's 100% similar with itself, so that it's always going to be exactly identical to itself. And then you'll find the next few metrics will probably be like 99.9%, which are probably like derived from the original metric. And then as you go down, you'll see metrics that are more kind of not what, you might find ones that you didn't expect to be related, and that's where then you can say, oh, actually maybe the root cause, or maybe the next step in your troubleshooting journey is in one of those metrics. And you can get fancy as well. You can you can use dynamic time warping, and if you have different lengths of time series, you can do fancy stuff as well. Next one is related to alerts again. So can you give me more lead time on alerts? This one is basically an idea. If you can predict an alert storm before it happens, maybe that's useful. So predicting individual alerts should be impossible. Should be hard. If it is possible, it means you've got a misconfigured alert. And the idea here is the inputs are your metrics, are your alert. Well, your inputs could be your metrics, or it could be alert calculations, and your outputs are what's the probability of n plus alerts in the next T minutes. So in this example here on the screen, that kind of shows what we're thinking about. Is like there was a cluster of alerts that happened. We want to predict this alert storm ahead of time. And so if you have this like yellow line over time, which is the probability of the alerts storm in the next n minutes, then you could see that maybe at some point before the alerts actually happen, it passes some threshold where you say like, okay, the probability is over the threshold now. You want to actually trigger your own warning, which is that the model has signaled there's a higher possibility of some sort of alert storm in the next few minutes. And this is, the questions here are like n plus, what's n plus, and what's t minutes like. So how many alerts, how far out do you want it to be? And within what window, and then what accuracy is good enough. Like if we trigger it out, if it crosses this threshold 10 times, are you okay with it actually only turning out to happen then 5 times out of the 10, 2 times out of the 10? It's that these are like kind of parameters that you need to decide, like what's your sensitivity to false positives. And then obviously one other thing is this is the inverse. If alerts are predictable, this is like another way we could use ML to weed out misconfigured alerts. So if an alert is perfectly predictable, that's a problem because it's obviously just misconfigured and it should be ignored. So this is almost like if you turn this one on its head, you could use that as a way to kind of filter spam alerts basically. Next one is, what are the drivers of this metric? So this is a common one as well, where you're looking at some sort of time series, and you want to know like what's actually driving this time series. So the inputs here are again metrics, but the outputs now are an explanatory model of this metric. So again, you've got a target metric that you're interested in. So in this chart, the top metric is the one we're interested in, and we want to know what other metrics are actually driving that metric. And this is basically, if you do this, it can be a regression problem where you're using other metrics to predict the value of the metric, your target metric, and it's kind of like forecasting. But what we're looking for here is we're looking for an explanatory model. So we're not looking for just accuracy. We want to actually understand how well can we predict this top metric line with all these other metrics. And then also we want to be able to explain it. So we want to say, like, if you could only use 10 other metrics to predict this top metric, what would those 10 metrics be, and how good of a job can they do? And if they can do a really good job, then you basically have the drivers where you can say, okay, well, like the orange line here, I didn't really realize that the orange line and the red line are pretty strong drivers of the blue line there. You can see that when the orange line and the red line kind of have that spike, that's when it has most impact on the top blue line. And so that could be something that could be interesting that you might not, And again, this gets into human in the loop. We can't kind of run away with ourselves because maybe it's true by definition that the red line and the orange line are like correlated to the blue line, because that's their metrics are kind of, they're derivatives of the same underlying metric. So this is where you kind of need human in the loop, and you have to be careful about not getting too far ahead of yourself. And the hard part here is actually how do you package all this up into a way where the information is usable for a user to just quickly see, like, yeah, no, that makes sense. Oh, I didn't know that the red line actually does seem to be a good predictor of the blue line. Cool. I need to understand that that's what's driving the spikes here, say. And the models matter. This is where you need to have models that are interpretable. So there's different types of ML models you can use. Some of them you don't get this kind of interpretability, but you might get more accuracy, and then some of them they are just more interpretable by the way they're made. So the next one is, what should I look at next? This is sort of like a holy grail, and I don't have much. This is one of the hardest ones. This is a recommendation. So given the clickstream data, given what you're looking at, given the context of all like active alerts or whatever else you're looking at the moment, how can we recommend your next best action? Or how can we recommend your next chart, dashboard, whatever it is, whatever the context is we're looking at. And this is where we'd like take a recommendation engine approach. So given the context, what should they do next? There's less here because this is actually one of the hardest ones. There's lots of ways to operationalize this and frame it. I don't think anyone's really done it well yet, because it is a big, hard problem. And it might be that some of the new language models and chatbot approaches, and they might actually have part of the solution here. But there's a lot of that goes on under the hood to help them understand what systems you use, how to talk to each system. But this is kind of like, if you can solve this, maybe you can solve all other problems. So this is like the holy grail, but it's one of the hardest ones to solve, which is why I don't think it's been properly kind of solved yet. And the next one is, can you predict the future? So this is like a typical enough one, metric forecasting. can you take the inputs, can you predict the next few values basically? And this is just time series forecasting. Prediction accuracy is the most important thing here. We don't care how you get that value for the predictions. We just care if they're accurate. And the idea here is you should start as simple as possible. So start with the dumbest, stupidest model you can use, and then you can measure the inputs and outputs and actually build everything else that needs to go around it. So back to that, that chart with the ML being the little black box, have that be as simple as possible here. And then the question is what are you forecasting for? So there's no point in trying to, if you've got second level metrics, there's no point in trying to forecast for the rest of an hour ahead or something like that. It's just not going to work. So you need to be very kind of careful about what's the how far ahead are you predicting. Don't try and predict too far ahead; it won't work. And you need to match the level. So if you want to forecast at hours, then you kind of need to aggregate up to the same level before you can even train any models or do anything like that. And then the big question, the most important question here is what are you going to do with the predictions anyway? So a lot of people just get carried away trying to do metric forecasting. But the question is how are you going to use the predictions? And you really need to think about that first before you because it can be quite painful to do metric forecasting well. And there can be a lot of domain expertise that needs to go into it on the ML side. And so the most important question is how, even if we had a forecast that was 50% accurate, what would you do with it? How would you use it, basically? And have those conversations before you actually implement anything. And then the last one, so I only had 9 originally when I did the slides, and I said I'd think about number 10. And number 10 is turbo chatbots that are, everywhere now, basically. I don't have as much to say here about this. I'm a little bit I'm on the fence a little bit about should we all just stop doing what we're doing and start using chatbots for all of our ML features. I definitely think they can be useful, and we have a sort of a version of our own here that does kind of helps you understand alerts. But I'm not getting too carried away. But there definitely is something to it. So chatbots made it to be number 10 basically. I think that's pretty much it. I have there's some links there on the deck for some blogs, and we have a demo for Netdata. We have a demo. And there's also some of these things I've implemented myself in a little kind of crappy demo app. That's the second last link. And we have some blogs and all that sort of stuff. So yeah, and I'm Andrew everywhere. So feel free to kind of reach out to me if you have any questions. And that's pretty much it. Is there any questions? Go.
Hello. It's about the point 9. From your slides. I'm not into ML, so this might sound silly, but if inputs were combined with some information, wouldn't that increase the percentage, the rates that the forecasting is right?
Yeah.
Is this possible?
Yeah.
To combine metrics with infra, and if our data set includes different types of infra, or more reliable, more whatever.
Yeah.
So we can utilize those results.
Yeah, I should have said actually that's a good question, because typically, so in traditional time series forecasting, the whole challenge is all you have is the blue line, and you have to use the blue line to predict the next value of the blue line. And but in the real world, we have loads of other information. We have other metrics. We have, was the deployment just made on GitHub, and so for sure, yeah, you can use that, and it will help with the accuracy. So you have to be a little bit careful then, because the only challenge is then when you want to go and use that prediction, you now have to go and ask these other metrics, So if we use the metric itself plus maybe 10 other metrics, you have to then have them at prediction time. So if you need to do at prediction time, you might need to go and look up all these other metrics to make your feature vector to do the prediction, and that can then add latency and overhead. So, but it will be more accurate if you can use more kind of context, So yeah, no, definitely. Even alerts from your other systems, they might also impact the forecast, and they should be taken into account. But you do have to be careful that you never use anything in building the model that's kind of like cheating that just wouldn't physically exist at the time of the prediction, because maybe the alerts don't come in until 15 seconds after you've got the metric, and you'd be defying physics if you try to use them. Do you know? So that's the only bit you have to be careful about. But yeah, like definitely you should use more context.
Yeah, I think things that you could do, for example, is if you have a service that consumes messages from a broker, and you look at, if you look at things like how many messages are being processed, or even what is the backlog size, and compare that to the number of services that you have currently running that would consume those messages. If you in the past saw that it was problematic to be able to handle that kind of volume, a solution might be to scale up, and then next time around, if you see that the behavior scaled up is better, then you might scale up earlier to prevent the buildup of the backlog. But this is really complicated because you need to combine a lot of information that is, as he said, intrinsic to whatever your setup is, and I'm not sure if you can do it automatically.
Well, one thing it can be useful for as well is the ribbons that go around the forecast. You would be able to understand, like, I'm less sure about the forecast, so if it's a time of change, you shouldn't trust the forecast as much because the bands are after getting wider, That's where you could use this as well as like a confidence score for the forecast, potentially as well. It can be useful.
I'm thinking that if that confidence score is down, then it makes it less useful.
Yeah, it does, yeah. Yeah.
It's worth waiting more.
Yeah. Yeah,
than getting something done.
Yeah, definitely, yeah, and that's where like.
I was mainly concerned about can I provide a different, for example, infrastructure map of my platform and see different lines on the graphs.
Yeah.
So if I have many alerts for the last month,
yeah.
If I put some infra that I don't have, but I'm planning to change to,
yeah.
Will I see some different forecasting? Will I be able to see this?
Yeah, that's where typically a lot of the forecasting is in like capacity management, capacity planning, like not sort of, it's a little bit like medium term, like can I get a signal if I need to scale up my storage or my CPU within the next week, and maybe some scenario analysis like what you're saying, where you like, if I do this, so that's typically where forecasting is probably most useful for like observability or ops type stuff, It's
because sometimes we just wait for the disaster to happen.
Yeah.
Some region goes down.
Yeah.
Some resource quota reaches the limit. So by just waiting, if we can get
no, and some of the providers try and do some of this stuff where they'll aggregate up to like headline metrics overall of usage and try and forecast that, but it can become hard then, because maybe your change of your deployment is like one part of that sort of aggregation, and then sure, how can you pull it all together? So it's a little bit tricky, but yeah, it's.
And by giving more information to the model, how is the cost going up? Is it exponential, or is it based on your experience?
Yeah. Oh, it depends. It can depend on like the type of model you're using. So typically, the models that are pretty friendly for this are the deep learning models, where you just throw in a big spreadsheet of data, and it'll sort of figure out and do like same way it did with the text example. It sort of does the feature engineering for you. You can do the similar with time series, where you can just put in 100 time series and have it predict the next value, and it'll figure out everything. But then they tend to be the more expensive in terms of like if you need a GPU, and then expensive to deploy for latency or hardware costs. But so yeah.
Thank you.
Cheers. I think that's probably it, is it? Cool. Well, there's more. I have to run up to the AI panel discussion on the main stage, so I'm sure there'll be lots of turbo chatbot talk and discussion on that stage now in a few minutes. Thanks.